the medicine, the molecule, small molecule structure can also be derived from different other sources like zinc, Swiss doc, and some other websites or other databases. And finally, we have to make a list that these are the proteins that we are interested in, and these are the ligands that we are interested in. And then we can go for molecular. So the list we can prepare like this. Like this is the mucus hypersecretion has these many proteins. Like protein have they have a list of proteins like this. I can just quickly show you. Yeah, these are the proteins. Phosphodiesterase 4, human neutrophil elastase, human macrophage elastase, and the list go on. Okay, all these are the proteins, gamma secretase and all. These are all are the proteins uh, which are responsible for the secretion of mucus. So similarly, whatever disease or whatever clinical condition the scientist is interested in, those clinical conditions will be taken as a base, and then we will find out the protein, the list of proteins from the literature, that these are the proteins present or these are the proteins which is affecting the disease. Many a times it happens that these proteins can be received from the previous stage that we have just discussed, network pharmacology. Network pharmacology can also give you the list of proteins that you can focus on. Okay. Apart from that, we do not rely on network pharmacology only. All right. We sometimes we cross check the effect in string databases. Sometimes we cross check the effect in published papers also, and in the books also. Right. So we cross check it, and then we will finalize, we will decide that yes, this will be the protein of interest that we will be studying. Okay. So after we decide the protein of interest and the ligand can be more, it could be 1, it could be 10, it could be 1,000. Ligand can be any number, but protein should be 1. So the molecular docking, when you are docking the molecules, the docking will happen with one protein. So if you have, let's say, 5 proteins, you will do 5 dockings. So your study will be into 5. The time and efforts required will be into 5. So here we will be discussing about one protein for now to understand. So if you are taking, let's say, PDE4, this is the protein of interest. Okay. So what we'll do, we'll take PDE4 as a protein. 3D structure will be downloaded from the PDB, and then we will check the amount of ligands or number of ligands present in the phytoconstituent list. Okay, so Combratum species is giving you a list of phytoconstituent. Let's say 40, 50, 100 phytoconstituents are present, out of which phytoconstituent is actually effective. That we want to know, which phytoconstituent is more effective or more potent. So this kind of studies we want to understand. So some of the answers will be given by molecular docking. We will see it here. Structure based docking, these kind of questions can be answered. What is the probable 3D structure of my target protein if no experimental structure is available? Many a times it happens that homology modeling is not possible because the 3D structure is not available on the PDB database. Right. In that case, you can prepare 3D structure. There is another study, 3D structure preparation of the protein of interest. The second one is where are the most druggable binding pockets? Once you download the 3D structure from the PDB database, where is the binding pocket or where is the allosteric sites? So when I'll show you the image on the BioVia, I'll show you the binding pockets and allosteric sites so that a scientist will understand that how your drug or how your phytoconstituent will bind with the protein. Then which residue from the functional areas that contribute most to the binding and that could be targeted in mutagenesis studies. So the residues is like a selected amino acids. Okay, so the drug is not a binding or drug is not reacting interacting with entire protein. The drug is interacting with specific set of amino acids or a very small portion of the protein. The entire protein is not affected by the drug. So that small portion is a binding pocket. That is a functional area of the protein, and the drug will bind with that area of the protein. So those specific number of amino acids are called residues here. But those residues, which residue is functional, that we can understand. The next one is, how does ligand binding alter the conformation? That means when ligand will bind with the protein, the 3D structure of the protein will change. And how does it change, that we will see. I'll show you one a small video so that you will understand that how does the conformation will change. How does the molecule dance between the protein. The next one is, which molecules are worth synthesizing or isolating, right? Sometimes it happens that let's say Vinca alkaloids have 400 proteins, sorry, 400 phytoconstituents. Datura has 500 phytoconstituent. So out of those 400, 500 phytoconstituent, which one phytoconstituent is most effective? Or if I want to isolate and sell it, if I want to make a business out of it, so how do we isolate or how do we decide that which phytoconstituent should we target? So that can be identified by structure-based molecular docking. Okay, and which ligand is more potent or which ligand is more effective? In other words, we can identify this on the basis of docking score. Higher the score, higher the effective drug. This is how we will understand by the results of molecular docking. So this is the second type of question, what? As I said, there are three type of questions here: why, what, and how. So this is the what. Now coming to how. This is the extremely short protocol that I have tried to enlist here. This protocol is giving you idea that what is the flow of study, and at the end we will have top few ligands out of, let's say, 400 500 ligands. We will identify top 2 or top 3 ligands, top 5 ligands that can be used for simulation study, next level of studies. So this is the entire protocol. These are some of the protein. I'll show you all these results in software, so I'm not discussing it right now. Let me just show you the software. So here is the software. This is BioVia Client 2025. Our college has purchased this license version. You can see here, everyone can see the green and red lines. The the cyan color and the red lines. Cyan color is the beta sheets and the red color is a helix. You can see the structure, helical structure here, or even here you can see the spiral structure. So this is alpha sheets, alpha helix, and the cyan color, this one, the cyan color that I've just selected, which is highlighted in yellow, this cyan color is beta sheets, and the green ones are loops. The loops are those areas of protein which is giving flexibility to the protein. Okay, all the proteins are flexible to certain extent, and those flexibility is because of the loops in the protein. So 3D structure is available here. Now This is the docked result of 1BOF protein. This protein is a PDE4 inhibitor, and I've used it here. So let's say this structure, I'll just select the structure so that you will understand. This is the structure. Now you have to understand how does this structure is reacting with the protein. So the protein and the structure, between these two, the effect will be studied here. So we'll just go in the effects, small molecule. Okay. Now you can see the effect here. If I want to see aromatic effect, you can see here the more blue color is the aromatic edge, and the face is pink here. So face is nothing but the parallel to the aromatic ring. You can see here aromatic ring. So the face of aromatic ring will be pink or orange. You can see the orange, slight orange color, and that orange color is the face of the aromatic ring. Either it is above the plane or below the plane, and blue color is the edge of the aromatic ring. So if you want to understand the effect of hydrophobicity or aromatic effect, then you can choose this option. Now the second effect I'll show you is H bond, hydrogen bonding. Again, the pink color is the area where the molecule is having hydrogen bond donor, and the green color is having is the area where molecule is having hydrogen bond acceptor. So you can see the color here, green and pink color is available. Now the green and pink color should not be so intense. It should not be so light, and it should not be so intense. That means the molecule should bind with the protein and it should detach after some time. Okay, if the molecule is not detaching from the protein even after a long time, that means the protein and the drug is binding covalently, or their energy is so high that the detachment will be very difficult. And in that case, the toxicity parameter or toxicity criteria can be a problem. So the balance of intensity should be minimal or optimal. Then instead of hydrogen bond, let's say hydrophobic effect, the same thing happens. Gray color and blue color, hydrophobic effects are there. Now, one more thing I want to show you is which is the area where protein is reacting with the molecule. So I've added here one small circle. You can see the red circle here. Maybe if it is not clearly visible, you people can zoom it. From here, I can also zoom it. Let me do it this way. Is the circle visible to all? This is the circle. The yellow circle, if I deselect it, it will be red. So this is the circle. And when I remove the circle, I will understand that these are the areas, or these are the amino acids which is effective or which is binding with the molecule of interest. Now, when I will change the display style, this is the display style of alpha helix and beta sheets. You can see alpha helix here. You can see alpha helix, the red spiral, and the beta sheet cyan color here. From alpha helix and beta sheets, if I am changing the style, then it is the pure amino acid. The chemistry people will be more interested in this kind of structure, so that they will understand that which bond is happening where, right? The bonds between double bonds and triple bonds, or the the red endings are hydrogen bonds. They are indicating hydrogen bonds here. So these kind of studies can be easily done using different types of presentation. Now, the interactions can be also seen. Let's say the hydrogen bond interactions. If I want to see this interaction in 2D, then this can be the 2D interaction. This can be the 2D interaction. Let me take it this way. So here you can see the different interaction of aromatic ring. Aromatic ring have interaction at histidine, uh, 57 number amino acid, and 99B amino acid, leucine. So these two amino acids are interacting with uh, aromatic structure. If I am not interested in aromatic structure, let's say I am interested in hydrogen bonding, then also the same thing. We have to select it and then we will check the 2D diagram. Again, histidine and leucine, they are affecting hydrogen bonds. So this is how we can see 3D and 2D effects of the components. And this is the docking parameter. Now this results can be downloaded in an Excel format. You can see the Excel format here. This can be downloaded in an Excel. Now C Docker interaction energy is the one where we are interested in. The highest energy, the better the molecule, or the affinity is more intense with the protein of interest. So here I'll double click it. So you can see SEI, this is the co-crystallized ligand, which is having highest C docking energy, 49.93, right? And we can see there is a list of C Docker energy here and the list of molecules here. These are the list of molecules. These numbers are uh, numbers from the databases. The database have CAS numbers, and those database will have, sorry, not CAS number, it is PubChem numbers, PubChem IDs. These all numbers are by default, the software takes PubChem ID. So these all are PubChem IDs. So when you put the number in the PubChem, you will get the name of the molecule. So this is how docking happens. We have n number of studies here. We have force field, we have initial RMS gradient, we have charm energy, we have different types of dihedral energy, van der Waals energy, electrostatic energy, hydrogen bond, and so on and so forth. We have very detailed study here. So this is a small idea about molecular docking. Now coming to MD simulation. The simulation will happen with top molecules. Like here, you people have seen that there is a top molecule SEI and 107706. These are the two molecules. SEI is a co-crystallized molecule, so we can say 10776, and the second molecule will be this one, 3348. So these are the two best molecules we can use for the simulation studies. Apart from this best top two molecules, what we can do, we can include one molecule which is marketed in the which is already marketed, right? For example, for PDE4, the marketed molecule is roflumilast, okay, which is used in COPD. So roflumilast will be taken as a backbone molecule. So we will compare our result of simulation and docking results with the marketed molecule roflumilast. So we will understand that marketed molecule have docking score this much, and the ligand of interest have docking score this much. So if it is close, then we can say that affinity or effectiveness, or you can say potency of the drug will be almost similar. Okay, sometimes it happens that marketed molecule has less docking score and our molecule of interest has more docking score. That means the potency of our molecule will be quite high than the marketed molecule, right? So this kind of data or this kind of analysis can give the vision to the scientist that if the scientist have to go for patent or not, right? So this kind of uh, um, interpretation can be taken from docking. Now coming to MD simulation, this kind of questions can be answered. How do different candidate ligands compare in the terms of binding free energy from MMPBSA, MMGBSA? We will see this both of this in the later slides. Which protein regions become more flexible or rigid upon ligand binding? So we have seen the protein and the ligand when they are binding, when they are giving interaction, which part of the protein or which region becomes rigid, right? Many a times it happens that loop is involved in the interaction, and if the loop is involved, the flexibility is lost and the protein becomes rigid. So this kind of study can also be performed. uh, do critical hydrogen bonds and hydrophobic contacts persist throughout the trajectory? Trajectory means the time, the entire process of reaction or interaction. We call it trajectory in silico study. So trajectory is nothing but the process, maybe 100 nanosecond, 250 nanosecond. Those are the trajectory time that we are allowing the molecule to react with the protein. Okay, so which kind of study hydrogen bond hydrophobic contacts, which kind of trajectory is persisting? That means hydrogen bond is persisting or hydrophobic effect is persisting, ionic bonds are persisting, which kind of interaction is more. Okay, that kind of study can also be done. Then how does presence of membrane or cofactor or metal ion can influence the binding and stability? Now here, if you want to see the cofactor and metal ion, let me just remove all this. Give me just 1 minute. I'll reload again. Yeah. Now this protein, if I want to see the different cavities, you can see here different cavities. Now I have selected here receptor cavities, different receptor cavities where the protein can bind different molecules. Now everyone can see the spheres here. Let me select so that you can see. You can see this sphere. You can also see the another sphere. Then the another one. I am selecting few of them so that you can visualize it in a better way. Now you can see this molecule is not around the cavities. The molecule is at the superficial level. The molecule is not entering the cavities. That means these cavities, let's say these two cavities, if this cavity is blocked, then two loops are blocked. You can see here two loops are entering this yellow ball. If I deselect the ball, you can clearly visualize the loops. You can see the loops here. Yes. So these two loops, this is one loop, this one is one loop, this one is one loop, and this one, the green one is the second loop. So both the loops are available in this region. So if this ball is having, let's say, some iron, let's say calcium, magnesium, manganese, cobalt, some of the iron, and that iron is blocking the loop. If that iron is allowing uh, the loop to react with the iron and to form some bond, in that case the flexibility of the loop will be lost, and the flexibility lost means the protein becomes more and more rigid. And this is how the presence of membrane cofactor and metal ion can influence the protein in a different way. Now many a times it happens that the binding pocket, the some of the metal ion goes and bind with the binding pocket so that uh, actual ligand does not go inside. So this kind of reaction can also happen. Or the allosteric site like this, where the protein is the drug is binding on the one side, and the other side the allosteric site is available. So let's say some of the protein are active only in presence of ATP or only in presence of Mg+2. So those kind of allosteric sites are offered by the protein in this way. So a researcher will understand where is the allosteric site, cofactor or metal ion can bind with the protein. This is the small protocol, the compressed form of protocol for MD simulation. Now, MD simulation is the last stage. So you people will definitely agree with me that analytical parameters or analysis of the last stage will be quite extensive. So here the simulation analysis, I've tried to classify it in 6 different classes. The first one is basic stability and flexibility study. So after doing simulation, basic stability and flexibility study can be attained or can be studied by 1, 2, 3, 4, these 4 methods. One is studying RMSD data. You can see here the RMSD data is looking like this. The first image, left side. The red one is the protein, and the gray or greenish one is ligand. So here you can see that protein is moving in certain manner. Protein flexibility is present here to a certain extent, and the ligand flexibility is almost the same. Sometimes, let's say here the ligand flexibility is reduced drastically. Here also it is very less, but most of the times you can see in this area, let's say 80 nanosecond, nsec is nanosecond, 80 nanosecond approximately, less than 80, maybe 70 to 75 nanosecond, the flexibility is almost similar. So this kind of study can also be done by RMSD method, which is basic stability and flexibility study, so that we can understand that how protein and ligand is flexible during and before and after the reaction. Then root mean square fluctuation, we call it RMSF. The right side is RMSF, where the red lines are beta sheets and the white one is, sorry, red lines are alpha helix and the white ones are beta sheets. And which amino acid is giving reaction out of the beta sheets and alpha helix, which amino acid is giving interaction, that is denoted by green lines here, so that you will understand right from the residue index or amino acid number 0 to 350 which amino acid is giving effect or which amino acid is involved in the interaction is mentioned here. So the graph will give idea to the scientist that which amino acid should be targeted. Many a times it happens that homology modeling will be studied with modified protein. So one protein will be altered by some another amino acid. One amino acid will be altered in the entire amino acid sequence, and the same protein will be studied again, right? So this will help some of the mutations in the human bodies, right? Like some people are uh, mm, not able to digest lactose intolerant people. So which protein is mutated? So that mutated protein can be studied here. So this kind of study can be studied. Then radius of gyration, solvent accessible surface area, secondary structure analysis, all those kind of studies can be done. Then second one, interaction and contact analysis, hydrogen bond analysis, salt bridges, hydrophobic contacts, protein ligand contacts, and distance and angle. Yes, distance and angle will be like this. So once this is a murolol molecule, one of the molecule in the study, and which amino acids are reacting with that molecule. So distance and percentage, even the percentage is mentioned here, that murolol oxygen is reacting with aspartate 201 or methionine 273. So this distance and percentage, both of them is mentioned. So total Two studies we have seen here, post simulation analysis. One is basic stability and flexibility. The second one is interaction and contact analysis. The third one out of the six, binding free energy and energetics. So MMPBSA and MMGBSA, these two are the major one. Apart from that, variants of MMPBSA like GMX, MMPBSA, or MNM, WGMP, MMPGBSA, or peer residue energy decomposition, potential energy components, van der Waals electrostatic, and bonded, non-bonded energy profiles. These kind of energy study, or energetics, energy related study can be also performed. Then conformational dynamics and landscapes. Conformation is a 3D structure. So principal component analysis, PCA analysis, then FEL, free energy landscapes, uh, clustering MD frames, and Markov state models. These are the models, or these are the study which gives conformational effect, or which give conformational details of the study or of the talking. Then fifth one is diffusion, transport, and other properties of the molecule. So the drug molecule, how do they diffuse in the biological system? How do they get transported? Will it bind with the hemoglobin, or will it bind with any other protein, or it will be soluble in the water itself? So those kind of transport mechanism, diffusion pattern, and other things can be identified by mean square displacement, diffusion coefficient, channel or pore analysis, and time dependent RMSD. So these are the methods by which is giving us details about diffusion, transport, and other properties of the ligands. Then the last type of the study is quantum and electrostatic structure refinement. So many a times it happens that when the molecule is dancing during the simulation study, let me show you. The molecule is like this. So the software is trying to get the right confirmation of the molecule so that we get the maximum score of the docking. So the molecule which is giving maximum score, that will be the right confirmation of the ligand as well as right confirmation of the protein. But sometimes what happens that let's say the molecule is in sp2 hybridization. So in sp2 hybridization, a bit chemistry I am putting it in. Maybe ecology people will will be not comfortable, but it is very relevant here. If the drug is in sp2 hybridization, the angle between two bonds has to be 120. Okay, but in the dancing structure, the software has identified 119.5 or maybe 115 degree, which is giving maximum docking score, right? So those kind of uh, structure can be refined, or those kind of structure corrections has to happen, because those kind of position is not possible with the structure, right? If the structure is in sp2 hybridization, it cannot give 115 degree ever. So in that case we have to stop those kind of false positive results, and we have to refine the results again and shortlist the correct result, the true positive results. And those refinement can be done by quantum and electronic structure refinement. This is done by two things: either you can go for DFT study, or we can go for QMMM or oniom study. So DFT study is more prevalent. Most of the papers, if you see, they will have DFT study only, density functional. This is not function, it is functional theory. So this is two methods of quantum structure refinement. It is DFT and QMMM. So in DST, in density function, geometry optimization happens. Geometry means, as I said, the angle between the two bonds will happens, and the distance between two bonds. Right? If it is OH, the distance is different. If it is C double bond C, distance is different. C triple bond C, distance is again different. So that distance in geometry is optimized here. The second one is interaction energies on the basis of suppression error. That means the molecule, as I said, in docking, we are comparing only protein and ligand. But in simulation, we don't have only protein and ligand. We also have a third factor, which is biological environment. We call the biological environment in computational technology, we call the biological environment as a force field. So this force field is present around the molecule and protein. That means in the biological environment, we have protein, we have ligand. These two components are there. Apart from that, we have water. Okay, the major component is water. So water is a polar molecule, and in presence of water, more interaction can happen. Yes, so water is present here. Apart from that, major electrolytes are also present. There are 5 major electrolytes. Positive में sodium, potassium, and calcium, and negative has chloride and bicarbonate. So negative reinforcement, if you are involving, then bicarbonate and chloride will also be involved. And if you are selecting only positive ions, or you are selecting only the positive structures, in that case the sodium, potassium, and calcium will be involved apart from water. So here the more accurate interaction energies will be achieved. Docking will also give interaction energy. The C Docker energy and the lib dock energy score that we have seen in the Excel, that energy score will be achieved by docking also and simulation also. But simulation is more realistic because the environment is surrounded by water and other biological other components which is present in the biological fluid. So that correction in the energy will be done in simulation. The last one is frontier orbital analysis, HOMO-LUMO analysis. This reactivity descriptors or charge distribution, H bond, nature of H bond, these all details will be modified, will be included, and then the final energy will be arrived. And that final energy can give us more realistic data or more realistic interpretation for in vivo or in vitro studies. So this all study is performed just before preclinical studies, or you can say in vitro studies, right? So that you will understand that which right molecule can be reacted with the right protein. Okay, if the docking score is giving you very less docking score in the protein of interest or with the protein of with the molecule of interest, in that case you have to understand that you have to change either molecule of interest or protein of interest, right? So this is how it will save the time, money, and effort for in vitro, in vivo, and preclinical studies. Here is some of the results. This is SSE results, which is showing the red one is beta helix and the blue one is alpha, beta sheets. Blue one is beta sheets and the red one is alpha helix. This is called SSE, secondary structure elements. And here at the right side, the summary of all interactions are given, that which amino acid is interacting in which way. So this is all the summary of interaction. The trajectory I was discussing about is in nanoseconds. I said that it can be 100 nanosecond, 250. Sometimes some of the editor in certain good journals, they ask for up to 800 or 1000 nanoseconds also, if the trajectory images are not matching. So in that case, the number of seconds, the higher the time, higher the simulation time, higher the time of the software to run. Okay, let's say 100 nanosecond simulation. I have finished. I've done it with one of my faculty colleague, one of my sir, Dr. Reddy sir, and that 100 nanosecond, I think it was done in three days approximately, 3 to 3.5 days. okay, with good configuration of the system. Very good, excellent configuration of the system. Took 3 to 3.5 days for one protein for 100 nanosecond, right? So it take a lot of time along with the graphics card. So this is all about three different methods. We have discussed the three methods. The first one is network pharmacology. The second one is docking. The third one is simulation. And all the three we have tried with a small portion of demo so that you will understand that how does it happen and how to perform it. So this is the third one. How is really important. It takes really hands-on training and a long time and really uh, supportive AIT so that person can learn it. So here is the final scientific approach behind computational study. If a person is a student and or even maybe a faculty also, if a person is interested just to finish the study, okay, in that case, I would recommend that a person can collaborate with the expert and they can get the work done in a time bounded manner, right? Before you start the work or before you start collaboration, you can sit and decide that how much time will it take to finish the work. Otherwise, the work goes on and it will never finish. The second one is if you're planning to make a career in the computational chemistry or computational pharmacology, network pharmacology, and all, then yes, it is worth to learn these techniques, but it will take a long time with a good IT skill, right? Many a times when I was learning these techniques, either internet was not on, or the server was down, or the lane connection has some issues, or there are many n number of technical glitches. So if IT support is good, definitely it will make a difference. So this is the approach for the researchers, that yes, if you are looking for the career, you can definitely go to learn it the bit by bit. Like you can see here, this is the BioVia software. In macromolecules, you have n number of options here. In simulation, receptor ligand interaction, pharmacophores, small molecules, all these options, if you go and study, let's say sketch molecules, if anyone want to make new molecule or receptor ligand interactions, so each of the options you have to go for multiple times for multiple proteins so that you will understand how do they work and what is the impact of the study, how exactly you have to compare or analyze, and the data can be giving you interpretation only when you are doing it again and again for multiple times. So it is just like uh, hands-on software, not hands-on the technique, the hands-on the software. That is what the right word is. So yeah, this is what I wanted to say. And thank you so much. I think I was very fast. Forward.
No, it was really a wonderful session, Mr. Siddharth.
Thank you, sir.
And many things, even after 20-25 years of service, after listening all these things, we also thought that we are very back in pharmacology. Because really, it was a wonderful in silico technology and network pharmacology. Now it is time to learn all these things, which is a
Yes.
demanding areas. Thank you.
Yes.
Yeah,
Even it builds a rationale. Yeah, like some scientists do write uh, grant for different purposes, different
Yeah,
research.
yeah, yeah,
So
yeah, yeah.
it build a rationale that why do we do this. Like for
Yes,
example, someone is doing research on Ayurveda, so there is
yeah,
no rationale. The people will go on questioning that Ayurveda, we don't believe Ayurveda, or we are not accepting this. You have to get some proof. So
yes,
yeah, this techniques can give some rationale that
yeah.
it is backed by certain, at least some science.
It will provide maximum support for your study.
Yes, and even the approval of grants can be more faster, or could be like percentage of approval could be higher.
Yeah, yeah, right. Over to you, Manoj.
thank you very much, Siddharth sir, for delivering such an informative as well as insightful session. The practical approach and the clarity with which the complex computational concepts like network pharmacology by using cytoscape, the molecular docking by various tools and databases, and even what I most likely is those typical research questions to be asked to oneself. That will
Actually,
really.
those questions I faced when I decided my research project. So those questions are actually my questions.
This is what the
I know
experience seeks.
better. I know better, Siddharth.
Yes, sir.
These are certainly enriching our understanding and inspired participants, I think, to explore these tools in their own research. One more thing is here, we have with us our respected principal, sir. Even from his busy schedule, every day is attending all the sessions with the same enthusiasm that we are participating over here. If sir is there, I'd like to request Upasni sir to say a few words on today's session.
Yes, Manoj.
Yes, sir.
Yes, Mr.
Hello, sir.
Thank you very much for your lucrative lecture on various approaches of pharmacology research and the help of in silico methodology that is doing great thing in pharmacology research. I think all the teachers and researchers should understand this computational technology, in silico technology, and should incorporate these what you can say technological aspects in their research, because nowadays whatever research papers we find, they are now started including this part also in their research, and this will be grateful for the conventional pharmacologists to take the help of this technology in their research. Thank you very much, Siddharth ji.
Yeah.
Thank you, sir.
And even we are thankful to sir that sir has suggested to include this theme, integrated computational modeling in silico pharmacology, in this FDP. So it's now gives us great pleasure to present an online certificate of appreciation to Professor Siddharth Patel in recognition of his valuable contribution as a resource person for day 4 of this FDP-SDP. Sir, we sincerely thank you for your time, expertise, and support, and hope this will be continued in future also. Kindly accept this certificate as a token of our sincere gratitude, and we hope to continue this fruitful academic collaboration in future. Thank you, sir.
Sure. Thank you so much.
Thank
With
you.
this, we conclude today's session. I thank our resource person for accepting our invitation and contributing to this day 4 of this 5-day FDP over here. We look forward to welcoming you all tomorrow for day 5, the concluding day of this FDP-SDP. Thank you and have a pleasant evening.